This is Jack Jackson again. We're going to do a little addendum to the last video. In the last video, we saw that if we took a triangle here, that we could go through a series of steps and reflect it about one line, maybe two, maybe three lines, and we can get it to a congruent image. So we can start with any congruent image, and it doesn't matter how many it doesn't matter what the congruent image, where it is, how it's oriented, so forth. You can always map there with three or fewer reflections. So now the question though becomes, well, what about something more complicated? Let's say we have more vertices like a pentagon here, and here we have a congruent pentagon, once again, just like we did with the triangles. So how do we get from this one to this one? Could it take more than three? We know it's going to take three to get the A, B, and C to A prime, B prime, and C prime, but do we need more uh, reflections to get the others to work out? And we're going to see something interesting here. So once again, we just do the same steps. Take A to A prime, do the perpendicular bisector of that line segment, reflect over that, and we get this thing here. It will this congruent pentagon here, and it will fix A prime. And just as we did before, now if B and B prime, B double prime and B prime are not the same, take the line segment connects them and take the perpendicular bisector of that, reflect over that to get B prime. B double prime to map to B prime without messing up A. So you notice it doesn't mess A up when you do that, because that perpendicular bisector will go through that A. Okay, now we do our next rotation, our next reflection. If C triple prime is not the same as C prime, reflect over. Well, you can call this line two different ways. You can say it's the line that contains A prime and B prime, or it's the perpendicular bisector of the line segment containing these two, C triple prime and the original C prime image up here. And we do that, but look what happens. D prime is going to be mapped, D triple prime is going to be mapped to D prime up here, and E double triple prime is going to be mapped to E. So it really didn't matter what this thing looked like. Putting some more vertices on it did not change the fact that we only needed those three reflections. So as it turns out, it doesn't really matter there. You can always take any congruent figure and get it to a map to any other congruent figure with three or fewer reflections, not just triangles, but for any of them. So it turns out if we can take any triangle, particularly if it's a scalene triangle, and see what series of reflections, either 0, 1, 2, or 3 reflections, or one single isometry that gets you to the image, then the same thing will work for all the other vertices. It completely tells you how that isometry or that series of reflections, either way you look at it, how that maps the entire plane. So it turns out you really just need to only really keep track of 3 points. Now, if you just have 2 points, a line segment, there may be more than one way to map a particular line segment to another line segment. For example, it might be able to get there by rotation or by reflection, for example. So, or if there's a high degree of symmetry to the triangle, there may be more than one way to get from one place to the other. But in general, if you just look at 3 arbitrary points and can tell where they go, then usually that's enough to tell you where everything goes. So pretty interesting there.